Thank you, Julia. Thank you. So how different are these natural gas storage and CO2 geological storage? Let's look at the big picture of these industries. So this is a natural gas storage field. This is a CO2 injection field. And this is also a natural gas production field. In the big picture, it looks really similar. Of course, there are some differences. There are maybe more, but what we can shortly say is that natural gas storages, it has a long operational lifetime, longer than maybe most production sites, for instance. For salt caverns, it's also very high flow rates. There is a special property of salt that it's a viscoplastic fluid. It does creep. For CO2 injection, CCS, we have to consider much longer time frames, more than 10,000 years to be climate effective. We have some reactivity of dissolved CO2, of water with dissolved CO2 with cement. We have the low viscosity of supercritical CO2, which is which creates some fingering and some differences in the behavior in the reservoir. We have to be supercritical to be dense. We have to be quite deep. And we heard yesterday with Catherine, for instance, the effects of the Joule-Thomson cooling effect when you have a low pressure reservoir. And natural gas also has its own specificities. I mean, it goes deeper probably and deeper offshore. It has sometimes high pressure, high temperature constraints. You can find corrosive gases, etc. So they are very similar. There are small technical differences for each. This is what we can find. Maybe there are some other points for the technical similarities. So now how big is the experience in each of these industries? If we look at this report from GCCSI, there are today 27 facilities, commercial facilities in operation for CCS. There are today, if we look at CETIGAS global underground storage, gas storage report, there are 661 underground storages in operation. 3/4 of them are depleted fields, and then there are salt cavern sites and aquifers. So this is a number of facilities. It's facility. It can have different sizes. If we try to look at the size, then it's very difficult to compare. One possibility is to compare the flow rate. So I did this tentative estimation of converting the total capture capacity, which is 36.6 million tons of CO2 per year. And so it gives, in normal cubic meters, 50 million per day. If you compare that to what is the withdrawal capacity of the natural gas storage, it's 140 times lower. And if we look at how many years of experience we have, where the first big dedicated CCS injection site in Sleipner started in 96, 25 years ago. The first natural gas storage in the depleted field started in the US in 1915, and in salt cavern it started also in the US, in Michigan, in the 60s. So it is also a much older industries in natural gas storage. But still, these two industries are, very small when compared to oil and gas, and they take a lot of the skills, of the specificities from the oil and gas industry, which is today there is like 1 million oil and gas wells in production in the US alone. So orders of magnitude bigger. So now I will try to bring you two examples on how this industry can build on lessons learned. First, focusing on the salt cavern industry, storage industry, and then on the CCS one. So this is an example I've been quite involved in over the past few years. In the salt cavern industry, you have this community called SMRI, Solution Mining Research Institute, that is gathering a little bit everyone. Thank you. And it also funds research projects. In 2015, it launched a call for request for proposals to develop a database of past incidents. And I copy some of the text of the call. The idea was to provide the industry with lessons learned to support continuing development of maintenance and safety program. And it was a phase 1, and it focused on 3 events: leakages, overfilling of cavern, and blowout. So we answered this proposal, and I coordinated and participated quite a lot in these works. And we came out with the idea that in this relatively small industry, we found 21 events of leakage, overfilling, or blowout. And it's too small to make statistic, but it's small enough to be able to try to understand them. So the approach we had is to build monographies of each event, try to give a quite short and comprehensive as possible, technical summary of what happened. So this is what we done and published in 2017, and then we also published a paper in a journal 2 years later. And then there was a call too on the other part of incidents, which are mechanical events, but less specific. I will just give you an example of one of these 21 events and how it can be used. Oops. I'm stuck. There's a message on the screen. Oh, it disappeared.
Oh, I think it's complaining
it
about
works.
the internet.
Okay. So I just give you one example, and it's not cavern specific, so it could apply to storage in porous media as well. It happened in Germany in '88. The background is that a well was drilled in '71. A 40,000 cubic meters cavern was developed. It was used for ethylene storage. In '88, the operator observed the annulus pressure drop from 75 bar to 40 bar, quite large. And very soon after that, they started having eruption of ethylene water mixture. At first, so the well is here. Do you see that? Oh no, you don't see that. I don't know. Sorry. So the well is here, and you see here this where there is no more vegetation, eruption of ethylene. In a very in a clear alignment, and this continued several days until 60 to 80% of the cavern inventory was released. It was a blowout without ignition. It did not no fire. So summary of the investigation: first, they did an elevation survey. It revealed an uplift after the eruption. Thank you. So it revealed an uplift of 0.2 meters in all this ellipsoid era. And based on cracks on building, it was estimated that before the eruption, the uplift was 0.5 meters. And in a nearby well, a water well, they see ethylene entering just below a 25 thick clay sealing layer. So just below this layer, you see the big gamma ray here. So here they saw ethylene entering. And then surveys in the cavern well showed a damaged connection of the single cemented casing at 100 meters, 11 meter depths. So this was the cause of the leakage. And so the final analysis that this connection may have been leaking for years, maybe 5 years or 10 years, and ethylene accumulated below this sealing layer. This accumulation of ethylene created the uplift of the sealing layer. it created strain on the cemented casing, and at some point, the strain on the casing was higher than what could be borne by the connection, and the connection failed, and this created this very fast leakage, and that created these blowouts, and this alignment is then due to the pathways in the underground and the faults. So this is an example of one of the cases we summarized. We also analyzed what could be analyzed, so it all is based on public information. Among the 12 leakage cases, when a breach through the steel was identified, it was also always found at a place where there's a single completion, single casing cemented to the rocks. And it's related to slow processes like shear stress, corrosion. Sometimes it's very specific too. Often it's slow processes. And the practice today for new wares is that there is basically no more single barrier for gas caverns. And then we also see that there are two standards basically. In North America, they have two cemented casing down to the salt. And in Europe, there is one cemented casing down to the salt, and then there is a completion here. So it provides an additional barrier with some inhibited water here. And also we put a downhole safety valve in Europe, so we can close the cavern from the underground. And this is a fail-safe mode, so we have to maintain pressure to keep it open. And if there is a problem, if the wellhead disappears, and everything would be destroyed at the surface, it would close. So this is one example of how the industry evolved and the practice evolved based on lessons learned. Now my experience, small experience in CCS industry, much smaller than most of you. So in 2005, there is this report by IPCC on CO2 geological storage that is giving a big importance to CCS. It would be a major driver to limit climate change, as big as renewables. And everyone in this industry started considering CCS as a big option. And then the question was how to make it, how to ensure safety of this industry that would be big, that would be huge. And in 2009, the European directive proposed guidelines for CCS. In 2012, in France, the French administration, Risk Prevention Administration, proposed or asked, I would say all relevant institutes like BRGM, INERIS, IFP, École Polytechnique, etc., to propose a guideline for safety of underground CO2 storage sites. So that was in 2012. This is the year I joined BRGM, so I did not participate to that, but this was the idea, and that was what was driving this safety assessment in France. It's derived from ISO 31000 on the risk management ISO, not dedicated to storage at all. And based on this approach that you have a risk identification, risk assessment, risk mitigation, etc., and together with continuous monitoring system. So this was the basis, and where this is very different compared to what has been done in this natural gas industry. This is mostly ahead of industrial experience. It has been set ahead of experience. So to conclude, I would say that there are big similarities, I think, between these two industries. First, they are very close to a much larger one, the oil and gas one, and most of it, most of the components, the most engineered ones, like the wares, are benefiting from it. It uses these industry standards like API, Geostock. It uses knowledge developed in the various geoscience fields. It uses its ecosystem, academic laboratories, research institutes, service companies, engineering companies, etc. There are some technical differences, some differences as well in legal and permitting frame. Acceptability is not always the same. I've always been surprised that sometimes industrial activities like EOR are easier to be accepted than CO2 geological storage. About how we use lessons learned, I would say that the storage industry started earlier, and it started also at a bigger scale. There's more experience. There is also a few number of incidents, and these have made the industry evolve, and industry practice, best industry practice has evolved over the years using what happened. And it's similar probably to many other industries. Oil and gas is the same, and even automobile, aircraft. I mean, it evolved over the years based on feedback from experience, from incidents, etc. In CCS, I think there is much fewer experience. I don't even know whether there is a real incident that happened on the few dozens of sites that are at commercial scale today. And also there's a time frame that is quite long, and it needs probably more planning, because you need to consider what will happen in 1,000 years too, which is not the time frame of other industrial activities. And so I see that safety guidelines are mostly set ahead of experience. Last point is that anyhow safety will be a continuous process in all of these industries, and we have to continue anyhow to incorporate lessons learned from this industry for closely related ones too into the industrial practice. So this is it. Thank you all for your attention. Sorry for the inconvenience, and I wish it was still easy to follow.